Okay, now let's also talk about some of the other conditions which you would naturally see being applied to certain events, and they become very important in upcoming questions, which you will see in the upcoming videos. Okay, so let's talk about mutually exclusive events. So let's say there are two events, E1 and E2, okay, and we call them mutually exclusive. All right, so what this basically means is that there is nothing in common between the two events, right? So what I mean by nothing in common is also saying that probability that E1 and E2 happens, and I can replace intersection with E2 with and, as we discussed before, the probability both these events happen together is actually 0, right? And what this also means, if I talk about, let's say, a Venn diagram here. So let's say this is event E here, E1, and this is E2. So there is basically nothing in common. So there's nothing in common between the two events. This is first, there's second. So the probability that both of them can happen together is going to be 0. Also, what it means is if one happens, the other is not going to happen. So I'm going to write this. Okay. So what I mean to say is if E1 happens, E2 won't happen. And if E2 happens, E1 won't happen. Okay. So that's mutually exclusive events. Now let's talk about mutually exhaustive events. So mutually exhaustive events is basically, let's say you have a sample space, okay? And sample space, like I mentioned, set out all possible outcomes here. And if you can divide, let's say, sample space into certain parts, okay, so that they do not overlap, right? And if they don't overlap, what it means, we just covered. So there was no overlap here, no overlap, right? We had probability of both of them happening was 0. So we're saying, let's say you divide them into separate parts. Okay, and there's no overlap. Okay. So here what we see is basically there's a sample space that has been divided into 4 parts. There's part 1, part 2, part 3, and this part 4. So these events, they cover the entire sample space. And they're also mutually exclusive. Why? Because they don't happen together. There is no overlap. So let's say if I say this is event 1, E1, this is E2, this is E3, this is E4, then what you see is basically if E3 happens, for example, let's say if this happens, then E4 can't happen, right? And if E2 happens, others can't happen. So this is what I call as exclusive events, mutually exclusive events. They are mutually exclusive, but there's one more property here, which is basically that they cover the entire sample space, okay? And a more general definition is like this. So let's say if E1, E2, all the way to En are events, mutually exclusive events, mutually exhaustive events, sorry. And omega is your sample space. Then basically if you take E1 union E2 or union E3 all the way to union En, it covers the entire sample space. So let me just describe what I wrote. What I mean to say, what this means is either E1 happens or E2 happens or E3 happens or En happens all the way. So this is fairly obvious. Let's say you had n mutually exhaustive events, and they're by definition mutually exclusive as well. So any one of them has to happen. Why? Because if you take any outcome, it has to come from the sample space. And this outcome, if it's coming from one corner of the sample space, it has to lie in one of these mutually exhaustive events. And therefore, one of them has to happen, right? But when you talk about either A happens or B happens or En happens, either E1 happens or E2 happens all the way till En happens, what you're basically covering, you're covering all possible outcomes here, and therefore that you get what you call as a sample space here. So here what you see is you get a sample space if you cover either any of these mutually exhaustive events happen. Okay? So any or. So this union is very important. So now in terms of probabilities, this becomes equal to probability of E1 union E2 union E3 all the way till union En is going to be equal to 1, right? Like I just said, if you take any outcome, it has to come from one of these events. And we were saying probability either even happens or E2 happens all the way till En. So one of the events has to happen. Therefore, the probability is going to be 1. Okay. The other way to write this is, so I'm just going to write this thing inside in a more mathematically apt form. And this is using this denotation. So what this basically means, it's a union, and this can be expanded. This thing can be expanded here like this. So it's E1 union E2 union all the way to union En. Okay. All right. So many of the times what you would see is these mutually exclusive and exhaustive events, they come in one go. So what you would hear is something called mutually exclusive and exhaustive events. So like I mentioned, if it's mutually exhaustive, by definition, you should know it's also exclusive. But they make it more explicit, and usually you would see it's mutually exclusive and exhaustive. Okay, so let's say you have n events, again, E1, E2, all the way till En. All right, and we call they are mutually exclusive and exhaustive events. All right, so in other terms, for all I not equal to j, if I take two events, EI and EJ, and I take an intersection on them, it's got to be phi. The set is going to be empty. What this basically means is you take any I or j, which is not equal to each other. So for all is that means for any, okay? I not equal to j. So we're taking different events here, and because they're mutually exclusive, the intersection of their two events is got to be empty, okay? In terms of probabilities, the probability of intersection of EI intersection EJ has to be equal to 0, because if one happens, other can't happen. That's the definition of mutually exclusive events. Okay, so I hope you're also following up with the mathematical notation. Now the other thing, this is exclusive property. Now let's also apply the exhaustive property. That is, the probability of union of all these events 1 to n is 1. This is again coming from the property we just reviewed of mutually exclusive events. Okay, now we're going to talk about inclusion exclusion principles to later in the video, but for the time being, you can take my word, and you can also remember this formula that union of these mutually exclusive and exhaustive events, which is represented by this formula, it's actually equal to the summation of the probabilities. And if you didn't understand what I just did, hold on, I'll just tell you what we're doing in more expanded form. Okay, so what's happening is, let's say this formula is this. It's E1 union E2 union all the way to union En. Okay, this is the formula. Now this becomes equal to probability of E1 plus probability of E2 all the way to probability of En. Okay, so this summation, this term, which is written in mathematically short form, is expanded like this. And what a summation is, basically it sums up the terms inside, and as you change the value of I here, PEI will change. So it's going to be probability of event 1 plus probability of event 2 plus probability of event all the way to probability of event 10, En, okay, which we have mentioned here. Okay, so now let's switch gear and talk about some other probability, which you would see a lot of times in these questions, is something called conditional probability. So what did we talk about in conditional probability? So let's say you have two events again, event A and B. Okay, there are two events. And the probability of A given B. What does this mean? This means probability of A given event B has occurred. So now we know something. Now we know that event B has occurred, and now we want to know what's the probability of A. Okay. Now think about this. If we had to just compute original probability of A, it would be something that we can compute if we knew some properties about event A. But sometimes what happens is we have relation between events, right? And if there's any relation, then the probability of A happening, given B has happened, is going to be influenced because their A and B are related, okay? And so that is where this probabilities become very important. Okay, so the formula for P, probability of A given B, or conditional probability of A given B, is probability of A intersection B or probability of B. Okay. Now one may think, okay, what if the events are independent? Okay, let's talk about that. So if A and B are independent, let's quickly derive the formula. So probability of A intersection B, probability of A given B is going to be equal to probability of A intersection B or probability of B And in independent events, we already know that probability of A intersection B becomes equal to probability of A times probability of B. Okay. And then you also have probability of B in the denominator, so it gets cancelled off. So what you see is probability of A given B is equal to probability of A. So this is conditional probability of A given B. This is unconditional property. Unconditional probability of event A. So what's happening is we're saying if A and B are independent, then the probability A happens, given B has happened, is actually equal to the same as probability of A happening, irrespective of everything. In other words, influence of B happening on A is actually nil, because it's the conditional probability of A happening given B has happened is actually equal to the unconditional probability of event A happening. Okay, similarly, if you had to compute probability of B given A, that's going to be equal to probability of B intersection A or probability of A. And if they were independent again, it's got to be equal to. So this is again the formula, you just have to reverse the terms. So again, if A and B are independent, then probability of B intersection A is going to be equal to probability of B times probability of A. And this again simplifies to the same thing. Okay. So now let's talk about some other things. Now, one interesting outcome of this conditional probability formula is, which this is the formula we know. Many of the times what we will do is we'll actually, move around the terms and we'll use this formation. Okay, so you can use this form. So many of the times if you have to compute the intersection of two probabilities, of two events, if you have to compute the intersection of two events, then this can be equal to the conditional probability of A happening, given B has already occurred, times the probability, unconditional probability of B. Okay, and this also might make sense intuitively. What we're saying is, hey, let's find the probability of B happening. So when you say PB, that means B, we are assuming now B has happened with the probability PB. And given now B has happened with probability PB, we multiply it with the conditional probability of A happening, given B has already happened. So if we do this, what we are making sure is AB happens and also A happens after B has happened. Okay, and this is nothing but also equal to the intersection of A and B, which is the probability that A and B both happen together. Similarly, if we have to compute B by A, this is going to be equal to B intersection A by PA. And you can also compute B intersection A as probability of B by A. Given the probability of B intersection A is actually equal to the probability that A intersection B, or A and B happen together, this formula becomes equal to BB given A times probability of B given A times probability of A. Okay, so if I have to compute this final formula of A intersection B, or A and B happening together, this can be equal to conditional probability of A given B has happened times probability of unconditional probability of B. And in other terms, if you use this form, so we use this form here, now we're going to use this form. So this is going to be equal to probability of conditional probability of B happening given A has already happened times probability of A. Okay, and this is the formula to remember if you have to remember something. Okay, all right. Now let's talk about the next one, which is multiplication rule. Okay, so let's say you have a bunch of events, E1, E2, all the way till En. They're all events. And we don't know too much about what's the relationship here between the events. They're independent or they're not independent. We don't know much here. But what we're going to do is we're going to apply some of the formulas we've learned just above and see if we can reformulate some of these probabilities. So we want to compute the probability of event E1 happening, event E2 happening, event E3 happening, all the way till event En happening simultaneously. Okay, so this is probability. Let me change color. This is probability all E1, E2, En events happen together. And if you had a smaller problem, then you can, of course, apply it to a smaller problem where, let's say, there are 2 events or 3 events. So this probability is going to be equal to what? This is going to be equal to, let me just clean up the board here. This probability is going to be equal to the probability of the first event happens. Okay. Then we now say, okay, event 2 also happens given event E1 has happened. Similarly, then we say, okay, event 3 also happens given E1 and E2 has happened. All the way, you keep multiplying till we get the last event, which is En, given En minus 1 has happened, En minus 2 has happened, all the way till E1 has happened. Okay, so let me just quickly talk about what I just wrote. So we're computing the probability all these events happen together. Okay, and intersection is when we say and E1 happens, E2 happens, and E3 happens, E4 happens. All of them happen together. Okay, so intersection is naturally the formula we apply here. Now, intersection, using the conditional probability formula, you can also reformulate this like this. We say, okay, let's first even happen, let it happen. Okay, we know it happens with the probability E1. Then we say, okay, let us also make E2 happen, given E1 has already happened. So E1 happened with probability PE1, and this has to be multiplied with conditional probability of E2, given E1 has happened. Similarly, now E1 and E2 have happened. So now we want to make E3 happen. So conditional probability of E3 given E1 and E2 has happened. Okay, and this means 3 events have happened now, and we want to make E4 happen. Similarly, we go on. This last term means all these terms before this one. Like if I say all these terms until here, they're going to be the probability that E1 till En minus 1 happen. Okay, and now they've already happened. So what we want is we want En to happen. So therefore, we apply the conditional probability of event given all these events from E1 till En minus 1 have already happened. Okay, so I hope this makes sense. This is another way to write an intersection formula, and again, this can be used in some of the problems. Okay, if I had to simplify, let's say if there were only two, events, so this formula would naturally become equal to probability of A intersection of probability B given A. This is what it would become in 2 events, and in 3 events it's going to be A, B, C. Let's say there are 3 events, we want to make them happen together. This is probability of A times probability of B given A has already happened, then probability of C given A and B have happened. Okay, all right. So now let's begin with the next topic, which is law of total probability. So this is an important topic because you will see applications of this topic in various questions as well. So we assume basically there are n number of events, let's say F1, F2, Fn. There are n mutually exclusive and exhaustive events. So if you don't know what mutually exclusive and exhaustive events are, so please make sure to basically look at the first part of the video where we basically cover mutually exclusive and exhaustive events as well, and some other basics of probability theory as well. Okay, so what I mean by mutually exclusive and exhaustive in terms of its implications is that if let's say there are 2 events which are not the same, the intersection of them is going to be phi for any 2 events, which is I and j, they're not equal. Okay, so basically what I mean is take any 2 events, I and j, such that they're not the same. The intersection is going to be phi, and as a result, probability of fi intersection fj, that is fi and fj events happening together, is going to be 0 for any event I and j which are not equal to each other. Okay, and the other thing is basically, so this is nothing but mutually exclusive condition. Then you have mutually exhaustive condition as well. That is, if you take a union of all these events, it will fill up the entire sample space, and as a result, the probability any one of these events happen, which is represented by this union of fi events from 1 to n, probability of any of these events happening is got to be 1, because this is all what the entire sample space is comprised of, and any outcome has to fall in one of these events. Okay, so this is basically nothing new, but there's nothing new so far. There's mutually exclusive and exhaustive conditions. Okay, now we'll start applying something new. So let's say there's an event E, okay, and we don't know the probability of event E. So we don't know the unconditional probability. This is also called as unconditional probability of event E. Okay, we don't know that. However, we do know conditional probabilities of this event along with certain other events. So let's say we're now working in the sample space, where you have F1 as the first event, second event, F3, all the way till Fn minus 1, and then Fn. Okay, so this is now the sample space. So this is now the sample space we had, and F1, F2, all the way till Fn are mutually exclusive and exhaustive events. This is exactly same as what we talked about here, right? So if you look at these guys, exactly the same stuff. So we have the sample space and it is partitioned into n separate partitions, which is represented by the different events, F1, F2, Fn, all these different mutually exclusive and exhaustive events. And they also cover the entire sample space and there's no overlap, okay? Now, when do we use this law of total probability? When we use it when we do not know the unconditional probability of event E. So this is not known, but conditional probabilities, right? Conditional probabilities is known. That basically means, let's say E was an event, something like this, okay? Now this guy overlaps F1, it overlaps F2, it overlaps F3, okay? And we want to compute the unconditional probability of E in this world. It's going to be hard for us because we don't know beforehand, but however, we do know the following things. We do know probability of E of F1, we know probability of E of F2, so on till probability of E of Fn. Okay, and as you can see, it's probability of E of F1, F2, and probability of E by F conditioned on F2, probability of E conditioned on F3 is got to be something greater than 0, but as it moves to other events like probability of E given F4 and so on, it's got to be 0. As basically the diagram is just showing that it lies, in F1, F2, and F3 only. So we can use these if you know the conditional probabilities, right? And unconditional is not known. That is where you can use this law. And this law basically states that unconditional probability of E is equal to probability of E happens with F1, or probability of E happens with F2, or probability of E happens with F3, all the way till probability of E happens with Fn. Okay, so what are we doing here? Why are we doing this here? So what's happening is, we know that in this sample space, there are n mutually exclusive and exhaustive events, okay? So if one happens, others can happen, right? And we also know that E is another event that happens in the sample space, okay? Now, given we have information about the conditional probability of E conditioned on these mutually exclusive and exhaustive events, we know that if E happens, it can happen with either one of these events, okay? And we just compute the probability using this formula. What we say is, okay, the probability of E it will happen is if it happens with F1, okay? And if it happens with F1, it cannot happen with others, okay? But that being said, it can also happen with others, but not at the same time. That's what I mean. So it cannot happen at the same time with F1 and F2 as well, okay? So here you may see that E can happen with F1 or F2 or F3, but it can't happen with F1 and F3 at the same time. Only one of them is going to happen. So let's say if F1 happens, then we compute the probability of E happening with F1. If F2 happens, we compute the probability of E happening with F2. If F3 happens, we compute the probability of E happening with F3 and so on. And this may be clear as well, because if, let's say I say probability of E intersection F1, this can be written as probability of E given F1 times probability of F1. And if you understand the interpretation, what we're saying is, let's say F1 happens. Then we compute what is the probability E also happens with it, okay? And this is precisely what we're saying here, right? Only one of these mutually exclusive and exhaustive events is going to happen at a time, right? So if F1 happens, we compute the probability of E happening with F1 using this, right? And this is basically, because in short, it can be written like this, so we place it here, okay? Similarly, F2 could happen. If F2 happens, we compute the probability E happens with F2, or F3 can happen, so on. Okay, so the underlying structure is this disjoint. I don't know why I'm saying disjoint again and again. So the underlying structure is these mutually exclusive and exhaustive events, Fn, and we condition on one of these events happening, and then we compute the probability of E conditioned on one of these events happening. So I hope this makes sense. Okay, So, and in case you didn't understand, that's perfectly fine. Just remember the formula, because that's probably the most important thing. Okay, so this can be written in short like this. I'm just now simplifying this because it's A or B can be written like this, probability of A union B. I'm just basically replacing or with a union. Okay, so this is union from 1 to n, E of intersection of E of Fi. Okay, and because they're disjoint events, it can be directly written as, F1, F2, and Fn are disjoint, or I mean to say they don't overlap. They are mutually exclusive. Similar words, you could take a summation from 1 to n, intersection of E with Fi. Okay, and now we bring in these conditional probabilities, and this can be written like 1 to n probability of E happening with Fi times the probability of Fi happening. Okay, so I hope this is easy, and this is what the final formula is, what you should definitely remember. This law of total probability. Here there are a few assumptions here. One is you have F1, F2, Fn, which are mutually exclusive and exhaustive events. So these are assumptions. Okay, and mutually exclusive and exhaustive events. Second is the probability of each of these events is greater than 0. So you don't have any event which is basically redundant. I mean to say, because it is present in one of these n events and it doesn't happen. Because if it's probability 0, it doesn't happen ever, right? So probability has to be greater than 0, and naturally it has to be less than or equal to 1. And then the next thing is we should also have finite number of partitions, right? So n has to be finite. If n is not finite, then basically you get into another realm of mathematics, which is measure theory, and that's where I think it's out of scope for us at the moment. Okay, so these are the assumptions. So if ever you have to apply law of total probability, you have to remember these guys, right? And the assumption, right, you have to remember this. First, mutually exclusive and exhaustive n events. Probability of each of these events has to be greater than 0, and the finite number of partitions. That is, n has to be finite. All right. Okay, now let's talk about one of the very important formulas that we use a lot in these in questions. That is basically Bayes' theorem. Okay. Again, we have an event E, which is going to happen in our sample space, and we have different events F1, F2, Fn, mutually exclusive and exhaustive events. So this is very important. Whenever you're applying Bayes' theorem, you have to understand there has to be n or some mutually exclusive and exhaustive events, and then there's another event E, which is our subject event, which we want to investigate more on. Okay, so we say the probability of Fj given event E has happened is probability of E given Fj times probability of Fj upon probability of E. This is the basic formula. How did we come up with this? Let's talk a bit more about this. Okay, so here we're changing something else. We have a sample space. There are n exhaustive, mutually exclusive and exhaustive events, and there's an event E. And we know now event E has happened in this world, and we want to compute the probability that one of these Fj is one of these mutually exclusive and exhaustive events. Fj, what is the probability that Fj will also happen given E has happened? This is what is precisely being represented by here. E has already happened. What is the probability Fj would also happen? Okay. And something on the right hand side, let's say first how we come up with this formula. So if you compute the condition, apply the conditional probability formula, this becomes equal to Fj intersection Fe intersection E times probability of E. And now this can be written like this as well, because A intersection B is B intersection A, or event A happening with event B is also same as event B happening with event A. Okay, and now we use, for this guy, we're going to use a conditional probability formula back. So this is going to be equal to probability of E given Fj has happened times the probability of event Fj happening divided by probability of E. And if you look at these two terms, they're exactly the same. Okay, so nothing, what we did, basically we applied the conditional probability formula, then we reversed the intersection, which is A intersection B is same as B intersection A, or any two events happening, A happening with B, B happening with A is the same thing, and then we applied the conditional probability formula back on it, and we got this formula. Now, what is so magical about this formula? I think one of the very interesting things that happens is when you start applying law of total probability to Bayes' theorem. So apply law of total probability to Bayes' theorem. LTP is law of total probability. Okay, so we have probability of Fj given E is equal to probability of E given Fj times probability of Fj, right? That's the Bayes' theorem numerator, and in the denominator you have PE, probability of E, right? Now, if you remember the LTP, law of total probability, said probability of E can be written like summation from 1 to n intersection of E with the different mutually exclusive and exhaustive events in a sample space, right? So if you go back here, this is the formula we had. And of course, the more refined version is this one. So we'll apply this one. So we'll say this is equal to intersection 1 to n probability of E given Fi times probability of Fi. Okay, so this is just writing P probability of E in terms of law of total probability. Okay, now let's apply to Bayes' formula. Let's see what we get. I'll take a new page. So probability of Fj given E is probability of E given Fj times probability of Fj. The numerator stays the same. In the denominator, we have this summation from 1 to n probability of E given Fj times probability of, sorry, we have I here, Fi times probability of Fi. Let's quickly talk about this. So if you have an event E and there are a bunch of mutually exclusive and exhaustive events, F1 to Fn, then probability of any Fj event happening, given event E has happened. You should keep this diagram in mind. This is the most important diagram to think about. This is one sample diagram. You know, you have n mutually exclusive and exhaustive events, and there's an event E that can span across a bunch of mutually exclusive exhaustive events. Okay, so the probability that Fj would happen given E has happened is going to be equal to the probability that E happens when Fj has happened times the probability of Fj happening. So this is nothing but probability of E and Fj happening together divided by probability of event E happening. So this is probability of E happening. And using the law of total probability, we expand it in the terms of the conditional probabilities. Product of conditional probability of E given on the mutually exclusive and exhaustive events, Fi here, times the probability of this, you know, this event, one of the mutually exclusive and exhaustive event. And we sum it up. So basically what we're saying is, we're saying, you know, E can happen in one of the cases, right? So this is probability of E, and it can happen in one of the cases. Let's say if F1 happened, then what is the probability E happened? If F2 happened, what's the probability E happened? If F3 happened, what's the probability E happened? So on, right? So this is the total probability of E, and this is the combined probability of A, E, and Fj happening. Okay, so I hope this explanation of Bayes' theorem is clear. It's going to be very important when you want to compute, again, one of the underlying mutually exclusive and exhaustive events happening, the probability of it, when we know an event has happened in the sample world. Okay. One moment, what I will talk about is the assumptions. So what's the assumptions? First of all, we got to have the law of total probability assumption. So what are the law of total probability assumptions? We have F1 to Fn mutually exclusive and exhaustive events. Okay, we have, of course, the n has to be finite, so finite partitions of sample space. Or I could say finite number of mutually exclusive and exhaustive events, whichever way you want to call it. Okay, next thing is, of course, the probability of each of these mutually exclusive and exhaustive events has to be greater than 0. And finally, the probability of event which we're talking about, E, has to be greater than 0 as well. Otherwise, in the denominator, you will have issues, right? Because you're going to be dividing by 0, and that is going to lead you to some, division by 0 issues in terms of computation. So some sane assumptions. Okay, so again, these are the assumptions you should keep in mind when you are applying Bayes' theorem along with law of total probability. If you're applying this basic Bayes' theorem formula, I think it's completely all right. Or in fact, you know, if you have to apply any general Bayes' theorem on any couple of events, it's perfectly okay. You can do it. Probability of A intersection B is A given B is going to be probability of A and B times probability of B. And here you just have to make sure that that probability of B has to be greater than 0. So this is LTP assumptions. And this last one is basically what I call as the Bayes' theorem specific assumption. So you got to make sure the denominator probability is greater than 0. Okay, so we're coming to probably towards the end of the probability topic, but there are a couple of more things I just want to quickly talk about before we start Markov chains. Okay, so the first topic we have is independent, some more items on independent events. So I know we already discussed about independent events in our last video, and if you've not checked it out, please do check it out. Link is in the description. But just a few things. So if let's say E and F are independent, there are two events which are independent. Okay. This also means that E and F complement is also independent. Okay. And F bar is nothing but F complement. F complement. This is basically event F doesn't happen. This is nothing but this. Okay. So if you want to compute probability of E intersection F, this is going to be equal to probability of E times probability of F, because we knew about this independent events in the first video again. So I would request you to refer to it if you are not clear about this. But if you want to compute the probability of intersection of E and F bar, this is going to be equal to probability of E and probability of F bar. Now, the reason again is if E and F are independent, then E and F bar are also independent. And you can think about it like this. You know, we took an example that if you do a coin toss and, you know, if it rains on a given day, they're independent events. But you could also think about this in a coin toss if it gets a head. That's the first event. And the second event is if you get a rain on a given day. So let's say if I toss heads, is it going to rain or not? They're independent. But if I get a tails, which is opposite of, you know, getting a heads on a coin toss, or basically it's C. It's a complement of getting a head, because if you don't get a head, you get basically a tail. Then getting a tails on a coin toss and also raining on that days are also independent events. Okay, and therefore it becomes very clear that if E and F are independent, then E and F complement are independent. Similarly, F and E complement would also be independent. And the second thing I would say, if E and F are independent, or in other words, this is more like an English clarification. So if E is independent of F, this naturally means F is also independent of E. Okay, so they're both ways. All right, so this may be basic stuff, but you know, something good to remember. And I think the final thing we want to talk about is an inclusion-exclusion principle. So what is this principle? This is basically a formula to remember, and I think you may not have to use it a lot, but sometimes it can be useful. But it's good for, of course, for solid understanding of computing probabilities, especially when you have n events. So let's say there are n events, E1, E2, En. There are n events. We don't know anything about their about their properties, so they're not stated to be mutually exclusive or exhaustive. They're not. Nothing is stated right so far here. So they're just n events, right? So we want to compute the probability of E1 happening, or E2 happening, or all the way till En happening. And this is equal to probability of E1 union E2 all the way to union En. Okay? So what is this? So it may look like a dangerous formula, but I think it's fairly easy to understand and remember. So E1 union E2 all the way to probability of E union En is going to be equal to summation from 1 to n, probability of EI. So first you just take the unconditional probabilities of all these events, which is stated right here. This is the unconditional probability. You sum it up, and then you subtract from it the following things. I1, let me just write it and I'll explain it real quick. Okay, so the second term here is basically you have a bunch of terms. Now they are I1 intersection EI2. So you got to pick any two events amongst these n events, and you take an intersection. That is basically you take an event which is EI1 and EI2 happening together. So this is the first event, this is the second event. I take any of these two events randomly from the n events. Okay, and when I choose these two events, I find out the probability that both of them happen together. This is stated here. And then one thing to note here is basically I find all these pairs. Okay, so this is basically when you see ei1 less than i2, it's just a way to make sure we don't double count. And if you basically look at a case of 3, this will become very clear. But what we're doing is basically in the first step, you have a lot of overlapping probabilities of any of these items happening. So for example, if you had just two events, the overlap part is this, and we used to subtract it by saying probability of A plus probability of B minus probability of A intersection B. And A intersection B is what is being captured here in the middle part. Okay, so this is the second term. So we take out the overlapping parts, but now we take out a lot of overlapping parts, so we have to add something back. And this is ei1 less than ei2 less than ei3, probability of ei1 intersection probability of ei2 intersection probability of ei3. And so on, this continues in negative sign, so the next term is going to be in some negative, and I'm just going to move on to the rth term. So the rth term is going to be minus 1 to the power r plus 1, i1 less than i2 less than ir, probability of ei1 intersection ei2 intersection eir. Okay, so this is the rth term. Again, this is the coefficient which you see here, minus 1 to the power r plus 1. And now we're choosing r items out of n. So this is r events, not items, r events out of. So this is r events out of n events overall. Okay, so we choose r of them, and then basically we sum it up. So we compute the probabilities of these all r events, and we, depending on what the value of r is, we add or subtract. And then we continue till we have the final term, which is minus 1 to the power n plus 1. And this time we have all the events happening together. Okay, so again, the last term is all the events happening together. So this is what you call as the overall formula for inclusion-exclusion principle, right? So I think a trick to remember this is simple. First thing is basically you have to understand, we start with a positive coefficient of 1, and then we go with minus 1, the signs alternate. The second thing is basically the number of terms also increase by 1. So you had just one term here, EI, and now you have EI1, EI2, and then we have EI1, EI2, EI3, and then, it goes on increasing till we have all the events happening together in the intersection here. And the coefficient, I think the other term is important to remember because that's where you can get the understanding of coefficients. And the index is something which is always in this form, that the index EI1 or the first event has to be less than index of second event, and it has to be less than index of third event, and so on. Okay, one quick point here is to understand in this rth term here, how many terms in summation would you have? So if I do summation from EI1, EI2, all the way till EIR, okay, and probability of EI1 intersection EI2 intersection all the way to intersection EIR, okay, so this would have NCR terms, right? Because we're gonna find the R events, and how many R events would we have? It's gonna be NCR, okay? So that's very much clear. All right, so congratulations. With this, we have completed the probability theory, and I think this will put you in a pretty good position to solve a lot of probability-based theorems, a lot of probability-based questions. And next we're going to cover Markov chains.